This is section 4.2, first and second derivative tests. We are going to learn what derivative tells us. We want to analyze a graph of a function because usually we are much faster as a species, we are much faster to make some decisions, fast decisions, looking at the graph than looking at the equations. Analyzing equations takes much longer than analyzing graphs. So we are moving towards that point where you will be able to graph any function without the aid of software. And the first and the second derivative test will be used to analyze the equations in order for you to eventually graph it. But it also will help with many other things. So let's see what are the aspects of the graph. So let's say you have a graph that looks like this. Clearly, there is a max somewhere. There is a min. Let me move. Let's say it's here. Let's say it goes forever. But then there are also some other aspects of this, like this is the increasing portion up to the max, and then you have a decrease, and then you have an increase again, right? So that will also be important. And then you would have this portion of the graph here, which would be called concave down. And this portion over here is called concave up. So concave down and concave up, two portions that are another part that we would discuss. So this particular section focuses on all of these concepts that you see there. First derivative test will pick up increase, decrease, min and max, and the second derivative will pick up concavity and also min and max, because min and max can be determined from both first and the second derivative test. So we don't have to mess with that calculation that I had at one point where we move a little bit and then compute. So now let's immediately define the first derivative test. Oh, and just I wanted to bring up the analysis, right? So you're looking at I picked the Apple stock, the Apple's stock. So you're looking at this line, right? And you're trying to figure out whether you should invest or you should not invest, right? So you might go and look at the number over here, and you would say, wow, they lost 46 cents, which means at the moment, right now, they are losing money. Their stock is losing money, so which means if I buy, I would be losing money, and obviously, why would you buy a stock where you would be losing money? But then you realize that, if you look at the graph, that these values jump all over. And obviously, you're not going to buy a stock at 11 and sell it at 12. Well, some people will do, but you try to see what is the trend over a longer period of time. So 5 days, 1 month, 3 months, 1 year, 5 years, and so on. So you see that as you are changing the time frame, right, you see the trend, which obviously means if you bought the stock right here at about 50 bucks, and now you still have it at 120, right, you are making 150% on your investment over 5 years. But if you bought the stock, right, if you go back and let's say you bought the stock 5 days ago, right, at this peak of $118 here, and you have it now at 116, you lost $2 per stock. So if you have, I don't know, 10,000 shares, you have $20,000 loss, right? So these are the things that you quickly determine from the graph. And then you would say the trend is decreasing. Sure, trend is decreasing when you zoom in on the 5-day period, but when you go to the 5-year period, trend is clearly increasing overall. So, well, it was increasing and then kind of tapped off and so on. But the trick is to understand that as a species, right, we are mostly visual. There are equations that will model this. That's not a problem, right? We can always model the past. We can try that to use to predict the future. But the easiest analysis happens when you are able to look at the graph and quickly determine increase, steady, decrease, increase, and so on. And that is your first derivative test. We already learned that in business, right, the word for derivative is marginal, right? So obviously they will use that a lot because the derivative shows the rate of change. So now going back to our simplified graph that we see here, we see the increase, decrease. So it's much smoother, obviously, functions are easier. And then whatever you learn, you just later apply on the crazier function. So what is this first derivative test? The first derivative test states if the first derivative computed at point A is larger than 0 on interval A sorry, this is supposed to be a C over here. So if the first derivative at some point C on the interval A to B, C is in between A and B somewhere, then the function f of x is increasing on that interval A, B. The second part says if the first derivative computed at C is less than 0 on the interval AB, then f of x is decreasing on AB. And that takes care of the first derivative test. The procedure for this, hopefully not an issue. We take the derivative, find the critical numbers, and then we'll make some regions, we'll pick test points, and we're done. So let's immediately use the first derivative test on the very familiar function, x squared. F of x equals x squared. So we are going to obviously pretend that we don't know how this function looks like, and we are going to compute everything about it. So find the first derivative, which is 2x, set it equal to 0, and obtain 2x equals to 0 from where x is equal to 0, and eventually 0, 0 as the critical point. Great. Now, first derivative test, f dt. I am going to draw a number line and place on that number line critical number 0. That splits the space into two regions, to the left and to the right. And I will choose two test points, in this case -1 and 1. You can choose, depending where the split is. You can have multiple splits. That depends on the number of critical points and asymptotes, but we'll talk about that. So now, as you can see, I have these two. And then These values, these test points are your C's. Those are your C's. The ones that you pick as test points are your C's. So the first derivative test is you take your C value, in this case -1, and you plug that in the derivative. Guys, title, first derivative test. Therefore, the test points will go into first derivative, not original equation. You use original equation to find the y values for any point you might need. The test values go in the first derivative, hence the first derivative test. So that's 2 times -1, which is -2, which is less than 0, which implies that on the interval -∞ to 0, function is decreasing. So what I'm going to do is I'm going to put this arrow of decrease in the region where -1 test point was. Now, repeat the whole procedure for +1. And we get that on the interval 0 to infinity, f of x is increasing, which will place the increase arrow above 1 in the region where 1 is. And now look how much effort takes to figure out that 0, 0 is a minimum. No effort, right? Has to be minimum. So this is how easy it is. Once you have the first derivative test done, immediately you can decide what your critical point is. And we're done. So now what do we know as a conclusion? And I'll write this in red because this is your solution for the problem. F of x is decreasing on -∞ to 0 and increasing on 0 to infinity. Now you know how the graph looks like. You will come up with the same conclusion, right? Looking at the graph. You know that the vertex of the x squared is at 0, 0. You can use your eyes to see that it's decreasing up to 0 and then increasing afterwards, right? So you can determine that when you have a graph. But what we are learning now is to determine all of that by not looking at the graph, but actually using the derivative and analyzing the function, the equation. And at the end, you know how x squared looks like, you know how to graph it, you know all of its aspects, and then you can cheat, right? But what are you going to do if I ask you what's happening with ln of x squared plus 1, right? You know how that graph looks like? Exactly, right? But you definitely can take the limit, you can figure out critical points, you can plug all of these values, and then do that part. So let's take a look at a bit spicier example than the one I gave you. So this is what your textbook thinks it's a good problem to try. So first derivative tests are problem 39 through 48. 39 through 48. Let's go with 41. X times the square root of 4 minus x squared. So you will find critical numbers first, and then we are going to do the number line, regions, pick test points, and then test those test points in calculus.
Right a little too because of the root. Oh, and then I get rid of it too.
Sounds like a Calc1.
They don't tell you if it's like the homework? Like if you can't play, like you can plug it in or anything.
Oh wait, do you got the right for this?
I've been having an interactive with it from
Oh man, that's a good doing the fantastic. Oh, really? No, don't do this really. Do the solution. The solution will for you. Yeah. Take all chapters. All the way about. So, you got one question. Yeah, and those grades will not be missing chapter grades for homework or for the they're not shown. You will see,
yeah, I mean, I'm keeping all of these, so at least I know I did it, so I can.
so you have a legal proof.
Something, something similar, right track.
Makes you feel better about yourself that you did some problems along the way. All right, we are at the 2-hour mark.
Wow. Likewise, you have lunch. Oh.
Because it comes out as a score line, right?
Discovery becoming outcome.
Well, yeah, once you put it in the product. Yeah, and then you just, so I probably, yeah, you can manipulate it a little bit to make it look nicer. And then figure out.
How do you pronounce it?
Negative x squared over the square root plus the square root.
except I don't know where
They probably were. Yeah, they do like common denominator, then they probably rationalize it. Maybe try to rationalize it and get the common denominator. That's why I would do that, actually. Because then you would have to consider they also switch the terms.
Okay, let's take a look at this problem. Oh, I forgot this. Let's take a look at this problem together. No, percentage is getting better. I did the previous problem, right? Now, fingers crossed. Copy the first, so the derivative of the second plus copy the second times derivative of the first. So we are experiencing a product rule, and then we also have the chain rule because that square root is not a basic square root of x. So now the half and the 2 will cancel. I have negative x squared divided by the square root of 4 minus x squared plus square root of 4 minus x squared. Now what I'm going to do is immediately get the common denominator. So just a little bit of algebra, black magic, so we can get this moving. Now, we never care how bad an evil denominator is. We don't care about that because once you set it equal to 0, denominator is gone every time. Don't bother foiling it, factoring it. Just forget about the denominator. No matter how nasty it is, just leave it. Because immediately, as soon as we set equal to 0, it's gone. It's the numerator that we actually have to be careful about. So we have 4 minus 2x squared over this square root of 4 minus x squared. And now we set this equal to 0. And we have 4 minus 2 x squared is equal to 0, from where 2x squared is equal to 4, from where x squared is equal to 4, 2, that's what I said, please pay attention, and then x is equal to plus minus square root of 2. So we have two critical numbers, so these are critical numbers. Where's my purple? So we have two critical numbers, and now we are going to do the first derivative test. First derivative test is we have the number line, and we have 0, we have negative root 2, and positive root 2. Now there is something important about this problem that you have to be on the lookout from functional analysis or analysis of a function standpoint, and that is the domain. If you observe the function carefully, and I'll write it here in blood, domain is negative 2 to positive 2. I hope you see that. Because if you try to use any value that is smaller than negative 2 or larger than 2, you will not be able to compute the square root. It will be negative value below. So that means, since domain is negative 2 to 2, that these endpoints here are negative 2 and 2. We can use negative 1 and 1 as test points on the inner intervals. And you actually have 4 intervals, right? There are 4 regions here that you have to consider. And in red, you have your C's. Those are your test points. So, first derivative test. F prime computed at, we can do negative 2, it's okay. So now, what do we get? Oh no, we can't. We get the 0 in denominator. We can't do negative 2. Nah. Can we pick? I don't think we can pick a nice value. We can pick 3/2. So let's pick negative 3/2 and positive 3/2. That's 1.5, and the square root of 2 is about 1.41. So 1.42, so negative 3/2. So the derivative is 4 minus 2 times negative 3/2 squared divided by the square root of 4 minus negative 3/2 squared. Okay, so now let's not go crazy with computing things. Look at the denominator. It's a square root of a number, and the value for that can only come out to be positive. So we don't have to worry about computing that at all. This calculation for the first derivative test only, I just want to make sure I forgot if I started the stream, good. This calculation for the first derivative test only is concerned with whether the value is smaller or larger than 0. So I don't have to worry about denominator at all because it's always positive. If you divide the negative by positive, you get a negative. You divide positive by positive, you get positive. So whatever the sign of the numerator is, that's going to be the sign for the entire calculation. Now what do we have upstairs? We have 4 minus 2, and then 9 over 4. That cancels. I think that's a negative, right? So we have a negative divided by a positive, which is a negative, which is less than 0, which means decreasing on the first interval from negative 2. What happened by negative? From negative 2 to negative root 2 is decreasing. Then we are repeating this calculation for negative 1 test point. That's going to be 4 minus 2 and then negative 1 squared divided by, you know what, I'm just going to put positive down there because we know the square root is going to be positive value. We are getting 4 minus 2, which is positive, divided by another positive. We get positive, which is the increase. Then f of 1. 4 minus 2 times 1 squared. Divided by positive. It's again the same situation. We get another increase. And then we have 3/2. is again negative over positive, which is negative, which is a decrease, and we have this. Great. So now we can see that we have a minimum at negative root 2 and whatever the y value is. And the maximum at x equals positive root 2. Function f of x is decreasing on interval negative 2 to negative root 2 union root 2 to 2, and f of x is increasing from negative root 2 to 0 union 0 to root 2. These are your answers. This is what your first derivative test is telling you. What's min, what's max, and then also the increase and decrease intervals. And those are all given over x values. Hopefully you are connecting that. This is an interval, which means x1, x2. From one x value to another x value. The function is increasing and then decreasing and so on. Cool? Yes? No? Is anyone with me? Yeah. This is the moment when I remember my high school math teacher from, what's the second, sophomore? Right? Second year? I never learned those names. I know that the freshman is the first, and then after that I confuse all of it. Oh, senior. I know senior is the last one because it's old people. Well, that's how I made the association. So in my second year, the student goes, but I don't understand. And he goes, you're not supposed to understand. We just taught you this. You got to go home and then do some homework problems and learn and read the book and so on, and you will understand. Don't worry about it now. You get home. You get it. Yeah. Makes no sense, and then you read the book and you watch the lecture again, and yeah, you try and try. The best calculus learning happens when you try to teach someone else. That's when everything is clear. You struggle through a concept to explain it to someone who doesn't understand it, you learn more than that person every time. Every time. Which is because you just try to make better connections and everything else. Killing. Huh? Oh no, I'm serious. I know. All right, so that's the first half. It's called the first derivative test. Now we're going to second derivative test. You know what we're going to do? Cut and paste the procedure. Except we're using second derivative. Everything is going to stay the same, except now our critical points are becoming the inflection points, and our, what do you call it? Increase, decrease will be concavities. So that's technically what is happening, and we will be able to use the concavity as well to show the min-max. Yes. So second derivative test. immediately the definition for it. So second derivative test. If second derivative computed at point C is larger than 0 on AB, function, well then, f of x is concave up on that interval AB, and if second derivative computed at C is less than 0 on AB, then f of x is concave down on the same interval AB. So now, what we are going to do here is, as I said, same procedure, except you go to second derivative, you set it equal to 0, and so on. So let's define the inflection point. So inflection point occurs at number 1, second derivative of C is equal to 0, or number 2, second derivative at C does not exist. So same thing like for the critical point. You see that? Except you're using second derivative. That's the inflection point. What is the inflection point? Inflection point is where the concavity changes. So inflection point changes concavity. And guys, every time when you have this does not exist, that means probably a vertical asymptote there. So inflection point changes concavity. And also I want to stress the, what else was there? Oh yes, what is concavity? So a piece like this, or these pieces separated, are all called concave down. So that's how curvature looks like. Pay attention to curvature in this case. And then if you have it like this, concave up. So let me draw x cubed. Clearly, concave up, concave down. Now we can prove this. The first derivative f prime of x is 3x squared, and then the one we need, which is the second derivative, is 6x. Set that equal to 0. There's your x equals 0, which leads into 0, 0 inflection point. If you do the second derivative test for it, it's the same thing as the first derivative test. Here's your 0. Pick your two test values. Those are your C's. Second derivative computed at -1 is -1 cubed, which is -1, which is less than 0, means concave down. On interval -infinity computed at 1 is 1 cubed, which is 1, which is larger than 0, which is concave up, 0 to infinity. See, that's the point. The inflection point, in this case at 0, 0, is where the concavity switched from being concave down to being concave up. Let's take a look at a spicier example, and that's it. There's nothing else. So procedure is identical for both. First derivative test, you do first derivative, increase, decrease. For the second derivative test, you will do second derivative and you will get concavity. That's all. For the first derivative, you have the critical points to separate between increase, decrease. For the second derivative, you have inflection points to separate between concave up and concave down. How about, so problems are 71 through 82. Let's go with 75. It says f of x is equal to e to the x times x minus 7. So take the second derivative, set it equal to 0 for inflection points. Once you have inflection points, do the tests. Well, the second derivative.
See you next week.
No.
Okay, let's take a look at this problem together and then do the review. So we need first derivative and then second derivative. This is a product rule, e to the x times this is derivative, so 1 plus derivative and then x minus 7. I will combine this, factor out e to the x, and we have x minus 6 now, because negative 7 plus 1 is negative 6. And now we take another derivative, which is going to be another product rule. Copy first derivative of the second plus copy second derivative of the first, so stays the same. And then we have the derivative to be e to the x and then x minus 5. We set that equal to 0 to find the inflection point. We do not get anything back from e to the x because it never crosses the x-axis, so no solution there. But x minus 5 will give us x equals to 5. So we have our inflection point at negative 2 e to the x. Right, when you plug in 5 in the original equation to obtain the y value, that's negative 2 times e to the x. So this is inflection point. Now we're going to do the second derivative test, which is going to have our line, and then the only number that we have to work with right now is number 5, splitting the region into two sections. We can choose two values, and I will choose two values that are easy to compute in the second derivative. So 0 should be easy to compute, right? Yeah. 0 is easy to compute because e to the x, right? So that's easy to compute. And on the other side, because I'm looking at the second derivative, and I just want to find something that's quick to compute. I can't use 5, clearly, but I can use 0, and I can use, how about ln 100? It's fine. ln 100 is definitely going to be more than 5. I hope. Yeah. Is it? 4 point, I was off. Okay, another 0. It's okay. ln 1000. It doesn't matter. You can pick whatever numbers you want. That's the key. It just has to be bigger than 5. So I picked ln 1000 just because I can. You can pick 6 as well, and then use a calculator. It's okay. So second derivative at 0 is e to the 0 and then 0 minus 5, which gives me negative 5, which is less than 0, which implies concave down on negative infinity to 5. And f double prime of ln 1000 is going to be e to the ln 1000 times ln 1000 minus 5. And it's going to be clearly larger than 0. Concave up on 5 to infinity. See, I picked these values so it's easy to compute. Ln, e to the ln cancel, so it's 1000 times the positive number here. I don't care what the value is. It just needs to be positive. So we have the concave up, concave down, and concave up. Done deal. Yes?
If we had x equals to plus or minus 5, it would be the domain would be minus 5 to 5, and there would be 4 possible unknowns.
Yeah, if you have more, sure. Yeah.
one solution, right? If there would be x equals to 2, so
You will have 3 parts to work with. Yeah, you can have any number of parts. Depends on number of inflection points. You can have infinitely many inflection points.
no, I'm saying that we have 2 value for x, right? It's 5 or 2. So how do we compute that?
What do you mean 5 or 2? There's
In one of the answer, e raised to x equals to 0, which gives no solution.
yes.
Supposedly, that was x equals to 2.
Okay, so then you would have three regions: negative infinity to 2, 2 to 5, and 5. And you would pick 2 to 5. You pick a number: 3, pi, if you like pain. Pi is good value to pick. Good. All right. Yes.
Where did negative 3 come from?
I'm sorry.
Where did negative 3 come from?
From original equation, when we plug in 5 to find the y value for our. So I plug that in the original problem. Anything else?
What's happening when x equals 6 and first derivatives become 0?
Well, you have a critical point, which means you will either have a max or a min at that point. Inflection point is a change in concavity where the critical point you are talking about equal to 0, 6 in this case, you are going to have a min or a max there. And when you look at the graph of this function, so we're learning how to graph this next, I was about to say next semester. Next class after the test, we will do 4.3 and 4.3, and I believe also 4.3 only is how to graph. So this would be first derivative test, and a second derivative test will be 2 out of 13 different things that we will compute and then draw the graph. Be a shopping list of things that we have to achieve. Great. Okay, stream off and then review.